Hi everyone. So today I would like to show you how we could find the expected value with a probability distribution table, as well as using techniques of probability to solve a question. This is a question that's extracted from the Oxford textbook, from the AISL textbook. Okay, now a question like this tends to be very vague, so we need to try to use different ways to unpack this question, and I'll show you how to do it. Okay, so please try to take notes along the way, and hopefully this will give you a little insight into how we solve questions like that. Now firstly, we know that this handbag contains three different items, which is 5 coins, 4 keys, and 8 mints. Now we're going to take two items from this bag, one after another, and there will be no replacement. Okay, and the question is basically find the expected number of mints that will be taken out of the handbags. Now the idea of this question is because there are many possible outcomes of you getting a mint. All right, and the number of mints that can be taken out from the handbag, they are all discrete variables, which in other words means that it's something that can be counted. We know the definition of discrete variable is it could be counted, is quantifiable. So we need to look at all these possible outcomes and to find the possible probabilities as well. Now let's just quickly do a quick recap, okay? To find the expected value, we do know that if we need to find generally taking the summation of all the discrete variable multiplied by the probability of each of the outcome pertaining to the number of mints. Okay, now I'll come to that shortly again, and I'll try to explain this using a probability distribution table, because this formula tend to get a little complex if we just simply try to apply this. Okay, but just bear in mind we need to find two things. We need to find all the possible discrete variables, and we need to find the probabilities for these variables as well. Okay, and what these variables are would be, generally we're looking at the number of mints from the handbag. Okay, but like I said, I'll show you how this works later with a probability distribution table, which will make the understanding of the question so much easier as well. Okay, and we can generally apply the formula later in this question. But before we do that, we're going to start unpacking this by looking at the probabilities first. But to find the probabilities, there's several techniques. Now in this course we have done things like the Venn diagrams, we have looked at the tree diagrams, we have looked at the sample space diagrams. I think generally if you look at this question, it seems like a tree diagram would be very appropriate, considering that we have three different items and we're taking two items from the bag as well. So what I'll do is I'll show you how to draw a tree diagram. Okay, now is it necessary to draw a tree diagram? I don't think so, but generally it will highlight or showcase all the possible outcomes, and it's generally, I would say, is a safer way to show all the outcomes, because when you start writing individual outcomes for the two items that's taken from the bag, you may miss certain outcomes, which can be very dangerous, especially in a test setting or an exam setting as well. So let's draw a tree diagram. Okay, now so first, this is going to be called item 1, and I'm going to have item 2. Okay, now this is going to be just simply coins, keys, and the mints. And what I'll do is I'll write the probability on the branches as well. Now this is going to be 5/17, because you have 5 coins and you have 17 items in the handbag. Now for keys will be just 4/17, for mints will be 8/17. Now what I will do for this as well, I'm just going to branch it out. Okay, C, K, and M, branch this out as well. C, K, and M. And I get this to be C, K, and M as well. Now, because this question indicates that there is no replacement, in other words, what it means is that if you take an item out, you're not replacing the item, which means that you're going to have one less item after the first item is taken out. So with the same idea, if you take the first one to be a coin, all right, if I have 5 coins, and if I take one coin out, I'll be left with only 4. And since I have 17 items in total, I'm going to subtract 1 from 17, and that would make the probability of you getting the second item to be 4 out of 16. And we do the same thing for the keys, which will also be 4 out of 16, because the first item is not a key, so obviously the number of keys remain the same as well. We do the same thing for the mins, which is 8 out of 16. Now, just for your information, you probably would have realized is that when you add up all these probabilities, they should kind of give you like 1. So it's kind of a way to verify whether if you're doing the correct thing on your tree diagram. All right. Now, let's move on to having the keys to be the first item. Now, that will make the probability of you getting a coin as the second item to be 5 out of 16. Now, for the second item to be a key, since I have taken the first key out, I'll be left with 3 keys. And this will be 3 out of 16. And similarly for the mins, this will be 8 out of 16. Now again, if I add these 3 probabilities up, it should give me 1. Okay, and finally for the mins, I'm gonna have this to be 5 out of 16 for the second item to be a coin. This will be 4 out of 16, and finally this will be 7 out of 16, because since the first item is a mint, I'll be left with 7 mints after the first one has been taken out. And of course I'll be left with only 16 items, so that's why it's 7 over 16. Now remember, if the question is asking for the expected number of mints taken from the handbag, we have identified that we need to consider 2 things, which is the number of mints that you could possibly take from the handbag, and we need to look at the probabilities of these variables. Now what I will do is I will simply draw a probability distribution table. I'm going to call this X. Okay, and not forgetting, X is basically defined as the discrete variable. And what is the discrete random variable that we're defining here? Which is the number of mints taken out from the handbag. Now, this gives us several possible outcomes, because number 1, I could actually have 2 mints that is taken out from the handbag. Because if you look at the tree diagram, I could possibly have the first one to be a min. I could also have the second one to be a min. So that this outcome will mean that I could possibly have 2 mins that is taken out from the handbag. Now, what I would do as well is, since there's only one outcome that gives me 2 mins, and we know that this is 8 over 17 and 7 over 16. Now we know on the tree diagram, to find the probability that the first item is a min and the second item is a min, what we'll be looking at is we're looking at the branches, and we're going to multiply the probabilities. Okay, so which is 8 out of 17 times 7 out of 16. Okay, now again, if you put this onto your calculator, you should get this to be 7 over 34. Okay, I'll just keep this as a fraction for now. Now, what we're going to be doing is, we also could consider that there could be no mins taken out from the handbag. Now, what does this mean? If there are no mins taken out from the handbag, we have to consider scenarios where you do not actually get any mins taken out from the handbag. So let's go back to the tree diagram again and identify which scenarios do not give you a mint. So if we look at that, I could see that the first item be a coin, and this, which is coin as well, this will not give me a min that will be taken out from the handbag. So we know that this is going to be 5 over 17 and this is 4 over 16. So what I'll do is I'll multiply the two probabilities out first. Okay, and that would give me 5 over 17, 4 over 16. So that would give me 5 over 17 times a quarter. So that's 5 over 68. Now remember, this outcome is basically coin. Okay? Now, but that's not the only outcome. We could also possibly could have a coin and a key. Okay? I could have possibly this outcome, which is a coin, and I could also have a key. Alright? And I'll look at 5 over 17 as the coin, and the same thing, which is 4 over 16. So we do know that 5 over 17 times 4 over 16 is the same probability that we had earlier with the coin and the coin. So that's going to also give me 5 over 68. Okay? Now, we need to try to identify if there are any more outcomes that possibly could give us 0 mins. So I could see, in this case, I could have a key and a coin. Okay? So I have to identify this outcome and I have to put this in as well. So this would be key and coin. So that gives me 4 over 17 times 5 over 16. Okay? And that would also give me 5 over 68. Okay, just simply put this onto the calculator. Alright? And finally, another possible outcome would be key and key, because that's not going to give you any min as well. So we'll be looking at key and key. So again, with the tree diagram, it is very, very helpful. So I'll take 4 over 17 times 3 over 16. Okay? And that's going to give me 3 over 68. Now, I got 4 different outcomes here. Okay? So what I'll do is, because I could have 4 different outcomes that actually gives me 0 mins, which is the discrete variable. And what I'll do is I'll just add up the probabilities here. Okay? Because I could have this outcome, or I could have this, or this, or this. Okay? And they are mutually exclusive. So if I were to add all the probabilities up together, I'm going to get 18 over 68. Okay? In other words, this would just be like 9 over 34. Okay? Now, that brings me to the final outcome, which is when would I actually just get 1 min? Again, if we look at the tree diagrams, there's actually technically 2 outcomes that's actually gonna, in fact, there will be 4 outcomes as well that gives me 1 min. So again, we need to look at the possibilities, because I could have the first item to be a coin. I could also have the second item to be a mint. So I'm just going to write this down. I could have a coin and I could have a mint. So that's one possibility. And I'll do the same thing again. I'm trying to multiply the probabilities out with the coin and the mint. So I get 5 out of 17 times 8 over 16. Okay? So it's 5 out of 17 times 8 over 16. Now that's going to give me the same thing again, which is 5 over 34. Okay? Now I could also possibly have the key, and I could also possibly have the mint. So I'm going to write this down. So I'll put key, mint. So that will give me 4 over 17 times 8 over 16. Okay? So I hope this is great for you so far. All right. So 1 over 2, so that would be 4 over 34. And we also have possibility where we could have the min and the coin. We could also have the min or the key. Okay, that will just give us just simply 1 min. So I'm just going to write down all the possible outcomes here, which is the min and the coin. And it's the same thing. I'm going to take 8 over 17 times 5 over 16. So that's going to give me 5 over 34. And finally, I have the mint, and I have the key here. And I'm going to take 8 over 17 times 4 over 16. Okay, so that's going to give me 4 over 34. Now, so what I'm going to do is I'm just going to add up all the probabilities together. Okay, because I have 4 different possible outcomes here, and they're all mutually exclusive, and that's where you add the probabilities up. So it's 9, 14, 18 over 34. Okay, now let me just consolidate everything again, okay, because it looks a little untidy here. So I have x and the probability for each of the outcome. For the number of mints, I got 0, I got 1, I got 2. I'll take the final answer here, which is 9 over 34. I have 1, which is 18 over 34. And finally, I have 7 over 34. Now, how do we know if the probabilities that we calculated actually is correct? Okay, and there is one way to check it. If we add up all the probabilities here, supposedly it should add up to 1. And I'm just going to do a quick check first, just to see if I'm on the right track. So if I add up the probabilities here, I actually get 34 out of 34, which is basically 1. So I know somewhat I'm actually on the right track, despite being a very tedious process of identifying the outcomes. But I guess we all believe that it's actually not exactly the most complex question, but it does take a little patience to unpack the possible outcomes. Okay, so now we're gonna bring the final touch to this question. Okay, now remember we started off by looking at what the expected value is basically taking the summation of the discrete variable multiplied by the probability of the discrete variable as well. And if we use this formula, this is how we apply this formula into this question. What I'll do is I'll take this value, which is 0, multiply by 9 over 34. Okay, and that essentially is just going to be 0. Now then what I'll do is I'll take 1, which is the next discrete variable, which is 1 min that could also be taken out from the handbag. The probability is actually 18 out of 34. So what I'll do is I'll take 1 times 18 out of 34. And finally, I'll do the same thing for these two numbers here. I'll take 2 and I'll multiply this by 7 over 34. So if I add everything up together, that's actually going to give me 32 over 34, which is essentially about 16 over 17. Now again, 16 over 17 may not be the best representation, so I'm probably just going to convert this into a decimal, which is approximately about 0.941 mins. So that's literally like the average number of mins that you will be taking out from the handbags. Okay, so I hope this video helps to unpack this extremely unforgiving question, but I hope this kind of builds up the confidence as well, as that a question like this, I hope is never going to appear in the DP exams, because I believe that this is usually going to be a more scaffolded question in the DP exams as well. But generally, this is how we will go ahead and do a question like this. So hopefully this video helps. So if you like this video, hit the like button, okay? And of course, please subscribe to my channel. All right, take care guys, and I'll see you again.